Thank you everybody for coming. My name is Trey Grainger. I'm the manager for search technology development at CareerBuilder.com. And today I'm going to be talking about enhancing relevancy through personalization and semantic search. So to tell you a little bit about me to get started, I've been at CareerBuilder since 2007. Been working on search for most of that time. Got a large team. A lot of what CareerBuilder does is search-based, so we've had a lot of experience with Solr. Enjoy coming to conferences like this to discuss that experience with all of you guys and to learn from you as well. Currently, I am in the process of wrapping up writing the book Solr in Action. I know a lot of you guys have a copy. If you don't, it's about 650 pages of awesomeness. I highly recommend it. It's going to be printed by the end of this year, but that's how much awesomeness you get when you purchase Solr in Action. So if you guys want to take a look, you can. Otherwise, I'll be referencing the book several times throughout the talk and talking about some other cool stuff as well. My main interests are in machine learning, recommendation systems, natural language processing. I've got a lot of experience with CareerBuilder, at CareerBuilder with large-scale distributed systems as well. I'm also the founder and chief engineer of SillyAccess.com, which is a gluten-free search engine and networking site. If any of you guys have to eat gluten-free or have family members who do, you might want to check it out. So here's the roadmap for today. Lots of stuff to cover. They decided to give me 75 minutes, which is probably needed. We'll see. So first I'm going to talk about how we use Solr at CareerBuilder, just to give you guys a taste of that. I'm going to talk about traditional relevancy scoring, what probably 90% of the people in this room actually use sort of out of the box with Solr or Lucene. I'm going to talk about advanced relevancy through the use of functions, and I'm going to talk about personalization and recommendations. I gave a talk 2 years ago in Boston about building a real-time Solr-powered recommendation engine. I'll be referencing a lot of that material in this talk as well, sort of giving a refresh on it, as well as talking about several new topics. Finally, I'm going to talk about some of the work we're doing in semantic search, a little bit different from the other semantic search talks you've probably heard here, and give you an idea of where we're going in the future. I hope by the end of the talk you'll have a great appreciation for the wide variety of things you can do in Solr to affect relevancy and how you may be able to take some of these techniques and use them in your own domain. So first about CareerBuilder. At CareerBuilder, our search platform handles about 2.5 million jobs every month. We have 60 million actively searchable resumes, so this is people predominantly in the US, but we have sites in Europe and Asia as well. This is people who've come to our site, said, take my resume, I want recruiters to be able to find me and give me job prospects. We have a lot more than those 60 million, but these are people who want to be contacted. We have about 300 Solr servers powering our entire platform. We've got a team that handles the infrastructure behind that, but it's fairly large in terms of Solr installations. We've got thousands of dynamically generated and unique indexes. Some of our job search index is one index. We've got one index for our resumes. A lot of times we have customer-specific indexes, so we get a new customer, they give us content, we spin up an index for them on the fly. So that's where the thousands come from. We also have that number is actually closer to 1 billion. I meant to update that. We've got about 1 billion documents in our platform as a whole. We might even be over 1 billion at this point. And finally, we get about 1 million searches an hour through our platform. Some of the things we do with Solr. One of the big categories right now is data analytics. So you can imagine we're collecting massive numbers of resumes, massive numbers of jobs. That basically gives us for the resumes, that gives us the supply of candidates in the employment market. And for the jobs, that gives us the demand for candidates. And we can do some very interesting things with that data, especially when we put it in Solr and enable keyword-driven discovery. This right here is a data analytics report for construction laborers that shows how easy or hard it is to hire them. We build all this based upon stats inside of Solr, looking at supply and demand and information about particular markets. A lot of faceting is involved here. We can break down candidate experiences by any number of factors, by company, location, education, demographics. We can show the overall supply for the market based upon any geographical location, breaking it down again by just about any facet. Market demand, labor pressure, which is supply over demand, how easy or hard it is to hire somebody. We can also do compensation based upon this information as well to give someone an idea of how much they should be paying somebody for a particular market. We do some interesting geospatial faceting, doing radius faceting, things like that. And those are some of the interesting data analytics techniques that we use. There's a lot more, but that's not what this talk's about. Traditional search, which, again, sort of out of the box with Solr, things you would expect us to be doing. Job search, come to our site, search for jobs. We power our autocomplete capabilities, resume searching, search for companies, search for applications for people who've applied to jobs. Lots of mobile experiences, various other, we've got about 15 different search-based products at CareerBuilder. Most of our platform is powered off of search in some way or another because we're a content company. We try to get that content out and match the right people with the right jobs and to provide information to employers about the job market, the employment market. Recommendations. So I mentioned earlier, I'd given a talk previously, and I'll talk some in this as well, but we use Solr as our recommendation engine. There was a talk yesterday about using Solr as a recommendation engine. We take a slightly different approach. We don't build matrices outside of Solr and then compile stats down and put them in Solr. We actually use Solr as our entire matrix. So when people apply to jobs, we pass that information back into the job so that we can link jobs for collaborative filtering. We also put attributes on the jobs and have attributes on user profiles that we can then use to search for things that we could recommend to those users. And I'll show you some examples of that in just a bit. But job recommendations and resume recommendations are the two kinds of information we tend to provide. Job recommendations, obviously, for job seekers. Resume recommendations for recruiters trying to find similar resumes or people whose resumes match their jobs. So moving on, this is more of an overview, hopefully. This was tagged as an advanced course, so I'm not going to go into this. I'm going to assume you guys have either seen this or you can look it up and read about it. But this is the default relevancy scoring algorithm in Solr and Lucene. It's predominantly based upon the first part of the equation, the TF and IDF. Those are the two factors you guys are probably most familiar with. The other stuff is useful but not worth going into. The TF-IDF at its heart is a measure of two things. The TF is how well a term describes a document. The IDF is how important is that term overall. IDF is measured based upon the rareness of the word, and term frequency is essentially how many times the term appears in the document. As an example, searching a job website, if someone searched the phrase an experienced Solr development team lead, or if this were in a document, you would be very, very unhappy with the search experience if all of the documents that had the word an in them, AN, showed up at the very top of your search results. Because that's not really what you meant. What you are really looking for is Solr, maybe team lead, development maybe, probably not experienced, but you would really expect the word Solr to show up at the top of those results. And so TF-IDF really helps that come into play. With traditional relevancy, you can also boost documents and fields. So in the job search domain, the job title and the skills associated with it, a job seeker or the jobs, are probably the most relevant portions. So if I'm searching for a job, I really want to match on those things as opposed to the job description or job requirements. I also want to match there, but maybe those shouldn't be weighted as high because there can be a lot more content there and they're less precise. It's also possible to boost documents and fields at both index time and query time. At query time, if you need to boost a particular document, you would do that with the elevation component, but there's lots of ways to do this in Solr. I'm not going to go into that. Read Solr in action, check out the Solr reference guide if you want more information on that. You can also make use of payloads. One of the things we do at CareerBuilder is instead of searching across multiple fields, where each field has a different relevancy weight, we actually, for speed, will put a lot of content in the same field with different weights. So the way we accomplish this is by using payloads. So for each term that goes into Solr, we tag that term with a bucket. And so in this example, I've got basically 4 buckets. Bucket 1 a blank bucket, my default bucket, bucket 3, and bucket 2. Bucket 1 happens to correspond with the job title field. Bucket 2 corresponds with the company field. The blank bucket is the job description because that's where most of the content is. I don't want to actually put a payload there if I don't need to. And bucket 3 is the experience field. So what we actually do is we take all of the content from each of these fields, we mash it together into one field, and we pre-pinned the sections of the field with a payload. We index the payload. It gets stored along with each instance of a term in the Lucene index. And then when we actually run the query, when we're calculating the score, we can inspect that payload, figure out what bucket it corresponds with, and then apply a relevancy boost to that bucket based upon the payload. So in this case, at query time, I can actually pass in, I want bucket 1 weighted with a boost of 10, bucket 2 weighted with a boost of 4, bucket 3 with a boost of 1.5, etc. And then at query time, I can actually dynamically modify those weights, just like I would be able to if I were searching across multiple fields using, for example, the edismax query parser. I can do the same thing using payloads with a single field. And we can also have hundreds of these. So instead of, if I want 100 different weights, I don't need 100 fields. I have one field, and I just use the payloads to search as many different buckets as I want to. Makes A/B testing really easy as well, being able to pass this in at query time. So all of that's great. That's all. I would still put all of that in the context of traditional relevancy, even the payload stuff. It's TF-IDF, it's scoring, it's algorithmic. It has no notion of the actual domain I'm working in. But what about domain-specific knowledge? These are some examples of common search experiences. You've got a news website where the popularity of a news article and the freshness, how recent it is, are probably some of the key factors that determine whether a news article should come back, how relevant it is. For a restaurant search, you really, really care about the location and probably the price range depending upon who's searching. For e-commerce, probably one of the driving factors is the likelihood that someone's going to purchase something. It doesn't matter how relevant the keywords are. What really matters is this person going to convert? Or are they going to give us their money? Are we going to be able to sell them something? Are we going to be able to show them something they want to see or want to buy? For movie searching, popular titles are probably more important than niche titles. Maybe they've got the same words in them, but you're probably really looking for a more popular title. And for job search, which is the domain I've got the most experience with, the category of a job, the salary range, and the geographical proximity are really, really important factors. In a nutshell, TF-IDF of keywords cannot hold its own against domain-specific relevancy. So the question is, how do you move from a world where TF-IDF of keywords is at the core, which is what you get out of the box with Lucene and Solr, to a world where domain-specific relevancy can take over? Short answer is through heavy use of functions. This talk in particular is about Solr, so I'm going to talk about using functions in Solr. You can do similar things in Lucene as well, directly. So here's a query for you. I'll dissect it. This is an example for a news website, which I mentioned earlier, really cares about the recency of a news article being published and also the popularity of that article. So what I've actually done here, you see my filter query at the top. I've used a variable substitution, which Solr supports, of my query. At the bottom, you can see my query is for street festival. So someone has come to my news website, and they're searching for a street festival. I've moved that into the FQ for a reason you'll see in just a second. In my query, you'll actually, if you can parse the syntax, you'll notice that there's no filters at all being applied in this query. This query is nothing more than a relevancy calculation. There's 4 components to it. The first component is actually executing the query function, which will get the keyword score of the query that was being executed. The second part is doing a geodis calculation, which is calculating how close the news article is to the person that's running the search. The third and is publication date. So when was the news article published? We're doing the reverse order, basically a reciprocal of the publication date. And then finally, popularity. The popularity, how many people have clicked on this news article, how many people like it, whatever our factor is to determine the popularity of the article. It's probably hard to grok from looking at this, but essentially each of these is banded but in a range of 1 to 100, I guess 0 to 100. And because there's 4 of them, that ultimately means that each of them can contribute about 25% to the overall relevancy calculation. The numbers don't add up perfectly because some of these have the ratios of these are out of whack in some cases. The ones that are using the scale function in Solr, it's trying to scale all the values between 0 and 100, but some of the others, they may not scale quite as nicely. You can see the location, the my query and the location, several of these things have been pulled out. The point has been pulled out like you would typically do with the geodis function. But what I've done here is I have removed from the Q parameter, I've removed the notion of it acting as a filter and have made the Q parameter only relevancy. And I'm still applying the keywords by supplying them an FQ. So the FQ is still applying the filter, but in the query itself, it's just doing relevancy. And you'll see why that's a... This is some fancier boosting that you can do. We do some of this at CareerBuilder. This particular case is for a job search. So what I've done at the top is I have made my query again. It's only the value of the keywords. And I've actually on this one turned cache equals false on the FQ. So if on the previous query you were concerned about, hey, what if I take all my keywords and put them in an FQ? Is it going to blow my caches up? You can turn caching off on this particular variable for the filter. So at the top, my actual keywords have been broken out into a variable. I've passed those keywords in as a filter with no caching on. And then in my query, all it's doing is calculating a score. Once you've separated your filter and query, it allows you to do some very interesting things, like you'll see in the second query. In this case, the first part of my query is executing, again, the query function. And if you can tell from the scale function and the map function, it's basically assigning 50% of the relevancy weight, up to 50% of the relevancy weight, to the keywords. The second line, the one that's got distance in it, is assigning up to 25% of the relevancy to the geodistance. And the third part is assigning up to 25% of the relevancy to whether or not a job shows up in the category for which I'm searching. And so you can see at the bottom I've defined the category as the job title of a Java developer. My keywords are Solr. There's my radius and my distance calculation. And what I've essentially done, if you've ever tried to add functions onto a Solr query yourself, you've probably seen that they might get out of whack. If you put keywords and then a function on, sometimes if you've got more keywords, the keyword score is going to be higher. If you've got a larger distance, it's going to be out of whack. It's hard to keep the two in sync. So by using something like a scale function, you can actually put a min and max on the amount of relevancy that comes from each factor, and you can add them up to basically form a linear function, if you want to think of it that way. You've got multiple variables, you give them each a weight, and you can build up your function based upon your domain. Once you've done that, the next thing you might want to take into consideration is the context. So in this particular case, if I hard-coded this query, where 50% of my relevancy comes from keywords, 25% from distance, and 25% from the category, what if those same rules shouldn't apply everywhere? In our case with job search, if we run some machine learning algorithms or just look at some basic stats, what we can see is, by the way, this graph is the willingness of a job seeker to move for a job. So it's based upon actual job seekers and where they're applying to jobs. And so what we see is that software engineers at the 55th percentile are very, very, very willing to move at least 500 or more miles to get a good job. Software engineers as a whole are not very location sensitive. Some of that probably has to do with remote working. Some of that probably has to do with people wanting to go to Silicon Valley from other parts of the US. By the way, these numbers are based upon the US, so my apologies to all of you in Europe and Asia. These don't apply to you. At least they may not. But software engineers are willing to move across the world. But on the far end over here, at the very, very bottom, food service workers. So people working at Burger King, McDonald's, bartenders, people working at nice restaurants. At the 95th percentile, they're not willing to work somewhere that's more than 10 or 15 kilometers away. So those are very, very different behaviors for different demographics. And at query time, I actually know those demographics. I know if somebody is searching for something in food service or if they're searching for something in software engineering. And because of that, I can go back and modify these relevancy weights. For a software engineer, maybe the distance has almost no weighting whatsoever. Maybe it has a little bit. For a food service worker, maybe it's very, very, very high. I can actually build context-aware relevancy ranking algorithms based upon what I know about the person searching or what they're searching for. Just to give you some more insight, this is a query for software engineers in Chicago. This is looking at their actual application behavior. And you can see that these are the places those software engineers are willing to move. Most of them obviously want to stay in Chicago. A lot of them want to move to the Valley. Some of them want to move to various other large cities in the US. If I switch to the food service workers at the bottom right here, that's what the circle looks like. They're not moving anywhere. You don't typically move across the country for a food service job. Therefore, our relevancy calculations should take that into consideration. Moving on, personalization and recommendations. So beyond food service workers not wanting to move and software engineers being okay moving, at CareerBuilder we actually have lots of information about the user, the specific user. So John lives in Boston. He's applying to jobs in New York. We clearly know he wants to be in New York for some reason, so we should be recommending things to him in New York. He's a sales manager, but he's applying to business development jobs. Irene's a bartender in Dublin. She's not going to move. She wants something within 10 kilometers of where she is in the same industry. Irfan, software engineer in Atlanta, Georgia in the US. He's in software engineering. He doesn't care where he has to move. He just wants to be at a big data company. When people start applying to jobs, we can glean this information based upon what jobs they're applying to. We can figure out what they're interested in, crunch that data, usually using Hadoop, build a profile, and then with that profile, we can generate a search for that user. So this bottom one, Jane, I'm going to use her as an example. She's a nurse educator in Boston seeking between $40,000 and $60,000. What can we do to help her find the right job? That's what we can do. We can form a query automatically without Jane having to type anything in for nurse educator jobs. If it's an exact match, I want to give it a higher boost. Otherwise, if it matches both terms anywhere, I want to give that a reasonable boost. Things in Boston, I want to boost the most. But if it's not in Boston and it's still in Massachusetts, maybe she'd be willing to move or maybe she would be willing to commute. I'm gonna include that as well. And by the way, this is her ideal salary range, so I'm going to give that a boost of 10 if it actually matches her salary range. What do you get when you run this query? These jobs. So she's a nurse educator, hopefully wants to be in Boston, but she'd be willing to be anywhere in Massachusetts. That's her ideal salary range. These are the jobs that come back. Clinical educator in Boston. Go figure. Nurse educator, Braintree. I don't know where that is, but it's in Massachusetts. It's not Boston, but it was the next best thing. Brighton's probably a little bit further out. By the way, all of these examples that I've just shown are actually in the Solr in Action book, and you can download. If you want to play with this, you can download the code and execute it, and you'll see the same thing. Shameless plug, sorry. You'll get a couple of those. So we generated this query for Jane. She's a nurse educator. She didn't have to type anything in because we already knew this information about her. What did we just do? We just built a recommendation engine. In Solr, usually people type in keywords and locations and other criteria. She didn't have to type anything in because we had a profile about her already built up, or we learned this information from her behavior on our site. We built a recommendation engine. So in a nutshell, what is a recommendation engine? Very dumbed down explanation. A recommendation engine is a system that uses known information or derived information from other known information to automatically suggest relevant content. Our example was an attribute-based recommendation. We knew things about Jane, and we searched for content that was tagged with those same things. But we'll see in a few moments that you can do much more than attribute-based. You can actually use user behavior to do collaborative filtering inside of Solr as well, which is how most popular recommendation engines work today. So before I go any further, I always like to take a step back and see how we look at Lucene and Solr in terms of a text search engine. This is the definition you get for Lucene on the Lucene homepage. That's generally put out there publicly. Is that Lucene is a high-performance, full-featured text search engine. That's true, but really, Lucene is a high-performance, fully featured token matching and scoring library which can perform full text search. Meaning, you don't have to do text search, you can do text search. Lucene, at the end of the day, is a matrix of terms mapped to documents. And inside of there, they're just tokens, and you're matching them and you're scoring them. So, in machine learning speak, Lucene is a multi-dimensional sparse matrix with very fast and powerful lookup capabilities. And in that context, you can think of each field as a matrix containing each term mapped to each document. When you think of Lucene that way, it opens up lots of possibilities for how you can make use of that matrix to find links between documents and to better match. So I'm not going to spend time on this. This is the Lucene inverted index example. I take a bunch of documents, pass content in, it's tokenized, put in an inverted index, which maps each term to the documents along with other various information in the postings format. Once I've generated that inverted index, I can run a search, something like a search for software engineer. We'll search in the job content field. It will look up the term software, find all the jobs that software, all the documents that software is found in. It will look up engineer, find all the terms the engineer is found in, and because my query was for software engineer, it will then find the intersection of those two, give me my documents back. In a nutshell, that's how the search engine works. Very fast lookups. It's basically like a giant hash table. Finds things, does the intersection, and you have your results. That's how the search engine can be so fast. That's a text example. But like I said a minute ago, Lucene's a matching engine, not just a text search engine. So when Lucene and Solr search text, they're matching tokens in the query with tokens in the index, not just text. What that means is that, like in our example with Jane, you can search for text, you can search for attributes, locations, results of functions, user behavior. So in our case, if people have applied to a job or if they've looked at jobs, we can actually flow that information back onto the job and use similar user behavior to recommend similar jobs. Just like Amazon's users who purchased this product also purchased this other product. In CareerBuilder, it's users who applied to this job also applied to these other jobs. So these are the different approaches you can take to recommendations in Solr. There's probably more, but these are the ones that we make use of. Attribute-based, which is what we did with Jane. Hierarchical. I can actually break down jobs into hierarchical categories and then do the same with users and then search across those hierarchies with different weights. Text similarity, using the more like this handler or something similar. And you can do concept-based recommendations as well. I'm not going to go into all of these. I went into them pretty in depth 2 years ago. If you want to refer back, you can go see that presentation. I've got a link to it in here. You can also do collaborative filtering, which I will show you in just a minute. I'll show you now. Collaborative filtering. So in our example before that we looked at, we have an inverted index with terms mapped to documents. Those terms are typically text or attributes, but in this case, my terms are users. So like I explained a minute ago, users who applied to this job also applied to these other jobs is the general concept we're trying to accomplish here. So what I do, I have a bunch of jobs, documents 1 through 5. I tag those jobs with a field, which is a user's, well, this is an e-commerce example, I guess, users who bought this product. I tag those users on the documents. This is what the inverted index looks like. It maps each user to the documents that they purchased. Then, if I want to actually generate recommendations, I follow 2 steps. First thing I do is I take the documents that I want to generate recommendations for. Maybe I've got a user and they have purchased both of these, whatever corresponds with both of these documents. So I'm going to pass in their documents, possibly do a facet, figure out what the top users are who purchased those documents. I do my lookup, I find the users, and based upon a facet or something similar, I get my top scoring results, my top users who are most similar to the current user I'm looking at. I can then take those users, generate a query for the users. So I want to find other users who have purchased this document or liked this document or applied to this document. And based upon that, I do a lookup again. Again, it's users mapped to documents. From that lookup, I use the built-in TF-IDF or whatever other relevancy calculation you want to use to generate a list of recommendations based upon this sparse matrix. And I get my job recommendations or my product recommendations back. That's, in a nutshell, how you do collaborative filtering in Solr. There's some caveats. If you've got massive amounts of data that won't fit into a Lucene index, you've got to pursue another option like Mahout or something similar. But for most use cases, at least for our use case, we can pull this off. And in our studies, it actually performs much better than Mahout. So building up to personalization, we started with TF-IDF, basic keyword relevancy. We talked a little bit about recommendations, building an automatic query. What about personalized search? I'm running a search. I don't want to see generic search results. I want to see something just for me, but I want to actually be in control. I want to enter keywords. What you do, or at least what we do, is from the first time a user comes to our platform, comes to our website, we start tracking information about them. They type in some keywords, we remember their searches. They type in, like we have their IP address typically when they come to visit us, so we can guess what their location is even before they tell us. Their searches, their clicks, jobs they've applied to, all of this behavior gives us an indication of what the user's interested in. And we can build up a dossier of this information based upon the user that we can then use for future searches and future recommendations. And in our case, we have a resume that the user gives us. In LinkedIn's case, they have a user profile, and in Facebook's case, they have massive amounts of personal information about users they can use to recommend similar content. But what you can do is start with what you have. So someone comes to our site, maybe all we have is their IP address. If they've run a search, we can recommend jobs to them based upon previous searches that they've run. If they, I'm sorry, that's really blurry. If they view jobs, we can recommend jobs to them based upon the ones they viewed. If they've applied to jobs, or if they give us a resume, we can now do, with applications, we can do collaborative filtering. With the resume, we can use the attributes in the resume to recommend content to them, to generate automatic searches for them. So no more about recommendations. That's the end of that. You can view the talk I gave before. There's a lot more in depth there. But once you have recommendations, the question is, why create a dichotomy? Why say, I can either have a user-driven search where they're typing information in, or I can generate a search for them and do recommendations. Typically, we've thought of recommendation engines as one class of problem and search engines as a different class of problem. But if you have recommendations driven out of your search engine, you can really combine the two. So as an example, say someone comes to CareerBuilder and we know they're a software engineer, either based upon jobs they've previously applied to or their resume or anything else we know about them. We know they're a software engineer, but they come to our search box and they just type in New York. Should we be showing them random jobs in New York? Maybe, you could make the argument. Or should we be showing them the same jobs but have the order different? Now, things that are relevant for software engineers are showing up higher. If they don't want to see those, then they can type in a keyword and override it. That's no problem. We're not taking the control away from the user. What we're doing is making the judgment call. Given the option between showing random jobs in New York and showing jobs that are probably interesting to you in New York, we're going to choose to show jobs that are probably interesting to you. Similarly, if a user comes to us, we've got their IP address, and they type in, they type a keyword search for nurse, the question is, clearly we're going to search for the keyword of nurse, but if I know that they're in Atlanta or Dublin or Chicago, should I not boost jobs that are in those cities higher because they're probably more interested in those? They haven't told us where they want to see jobs, and we're going to show them all of the jobs worldwide, but we can guess that they're probably more interested in things closer to them. And that's where you can really take this concept of recommendations, automatically generating a query, and user-entered search, and combine the two together. Semantic search. Next topic. So here's what I'm not going to talk about. I'm not going to talk about using the synonym filter, which if you build your own dictionaries, obviously you want to use that or something similar. That's very well covered in all kinds of documentation. I'm not going to talk about language detection, stemming limitization, multilingual search, or stop words, any of the sort of basic building blocks for semantic search inside Solr. Instead, what I'm going to cover is how we mine user behavior to discover synonyms and related queries, how we can automatically discover related concepts using clustering that's already built into Solr, some work that we're just starting on latent semantic indexing, which is a very exciting future, but we're not quite there yet. Document-to-document searching using more like this, and some different approaches to this document-to-document searching idea using foreground and background corpus analysis, something we've had a lot of success with at CareerBuilder. So first of all, automatic synonym discovery. There's lots of ways to do this. There's some interesting blog articles online about how you can take keywords, take the Wikipedia corpus, and try to extract out synonyms out of the Wikipedia corpus. In our case, one of the blessings of working at CareerBuilder is we have a lot of traffic. We have over 1 million searches an hour for jobs. So we can take the behavior of our users and really derive a lot of useful information from that. So our primary strategy for discovering this information is using map-reduced jobs, which mine the user searches to look for co-occurrence of search terms. As an example, you've got someone who searches for Java developer, they then search for J2EE. You've got someone who searches for registered nurse, and they search for RN, and then they search for PRN. You've got someone, again, who searches for Java developer, Scala, JVM. You expect people, if they're going to execute multiple searches, most of the time to be executing similar searches. That's not always true, but it happens enough of the time that we can mine the data. The other thing we can do is, based upon the jobs people actually apply to, we can look at what category each of those search terms falls within. So if someone searches for Java, and they're applying to jobs that are Java developer jobs, or maybe a better example is they search for Scala, they apply to Java developer jobs. We can figure out that there's a link between the two based upon the user behavior in searches and what they actually end up finding. And by running a map-reduced job and looking for co-occurrences of terms, we can generate really nice lists like this. So for the keyword RN, here's a list of some of the top terms that were searched for along with RN. Registered nurse, RN registered nurse, nurse, LPN. These aren't exactly synonyms, but they're highly related terms that we can then use to boost relevancy. We can add these terms onto a query as part of the relevancy function to make sure that I'm not searching for a document that has the two characters RN in beside each other. I'm searching for a document that has those two characters beside each other, but also is related to all of these other concepts that are tightly integrated. Same thing for accounting. I get accountant, accounts payable, finance, bookkeeper, controller, all things that are highly related to my initial search for accounting, but they're conceptually related, and I can search for all of these together as a concept, as opposed to searching for a single term, a single piece of text, which might actually find me documents that have nothing to do with accounting. They just happen to have that word in them. But they have the word account, and maybe I stemmed or limitized down to that word. Next topic. So this is a topic that I was really hoping that I would have a lot to report on when I got here, but we just started working with this, and I've had minimal success at this point, but I've also put in minimal time. So I hope maybe in a future talk to be able to talk more about this. Latent semantic indexing, the general idea is you build a matrix of all terms, you perform singular value decomposition on that matrix to reduce the number of dimensions. So in a very abstract case, you reduce noise words that don't add any meaning, and then for things like .NET, C#, VB, ASP.NET, all of those terms are very similar and probably show up in similar contexts. So if you reduce the dimensions down, those might all map into .NET, for example. And you can basically have the machine automatically build, let's call it a concept map of each of these terms by reducing all of the keywords down to a set of keywords that are highly descriptive and highly relevant within the domain. It's almost like building a brain, if you will, inside the search engine, or you build it outside the search engine and flow it into the search engine. There's lots of ways to accomplish this. I'm not an expert at this, hope to be one day, but that's the general idea. and it basically allows you to create a conceptual model of your domain space. It may not look that clean to the human eye, but when you use it for searching, it can do wonders. So I'll give a shout out real quick to John Berryman, I see him here, and Doug Turnbull. Is he? I don't know if he's here or not. But anyway, these guys have been doing some work in open source connections with latent semantic indexing. They've got some really interesting blog posts about it. I've fired up a few of their examples, and as far as I'm concerned, they're sort of the thought leaders on this right now in the open source space, at least those who are contributing code back and getting the ideas out there. So I appreciate your work, and keep putting it out there because I'm going to keep stealing it. Okay, so in addition to those ideas, what can you actually do in Solr now as it comes out of the box? One thing that is very, very interesting to me that we've made a lot of use of is clustering. So any of you who don't know, Caret 2 is a very sophisticated clustering library that is integrated into Solr. There's a clustering component in Solr. When you run your search, you can actually get results back that find related, let's call it related concepts, related phrases and terms associated with whatever you search for. The general idea behind clustering, in Solr at least, is, in this example, I searched for .NET jobs. The goal of the search engine is to find the most relevant content coming back. Here I'm just using standard TF-IDF. It's ranking documents that bring me back the top results. These aren't just links, though. These aren't just document IDs. These are actual documents that for some reason in this sparse matrix were connected. And what do I mean by connected? What I mean is that these all have things in common. For example, they all seem to reference software engineers. I didn't search for software engineer. I searched for .NET. But these things all seem to be about software engineers. They seem to be about developers. They seem to be about this thing called a C#. I don't know what a C# is, but a C# clearly seems to be related to a .NET. .NET developer, you get the idea. It's not just that you get scored documents back, it's that those documents are related to the thing you searched for, and there's probably other similar relations that you can derive if you look for them. So in Solr, I told you the clustering component comes out of the box. In solrconfig.xml, all you have to do is add the clustering component as a search component. You create a request handler. You add the clustering component as a component in your search handler. And once you've done that, this is all you have to do to generate clusters. You hit your request handler that you've defined that has the clustering component, run a query, say I want 100 rows back, you give it a title and a snippet field. The title would be some short piece of text corresponding with your document. The snippet would be a longer piece. You can pass the same value in for both, it doesn't matter. You indicate the desired number of clusters you want back, and let Solr have at it. And for this particular search, using our 2.5 million jobs at CareerBuilder, we find the top, what was it, the top 100? We find the top 100 rows, cluster the related terms in those documents, just like you saw a second ago in the .NET example. And these are the things that come back for my search for Solr or Lucene. So it's automatically found links between these documents for the terms developer, Java developer, senior Java developer. You see search in there. You see Hadoop engineer in there. So yeah, to clarify, the way this is working, in this example, I didn't cluster all 2.5 million documents. What I did is I ran a search. I asked for 100 results back, and then I clustered those 100 results. And so it's plenty fast for that. If you actually wanted to do full corpus clustering, you would want to do that offline. That would obviously take a really, really long time to run across millions of documents. It'd take a long time to run over hundreds of thousands of documents. But in this case, I'm doing 100 documents, and it comes back in less than a second. But anyway, you can see this list of terms, and it's not always going to be this clean. It really depends upon what data you're using. In our case, I'm using the job title to cluster on. If I tried to cluster on the full body of the job description, job requirements, I would get really noisy results here. But the job title is a fairly normalized piece of text. I can cluster the results there and get a really nice list of, effectively, they're not synonyms, but they're related concepts. And just like when I was describing the latent semantic indexing or the automatic synonym discovery where we found these relationships. And similarly here, I can add these terms on to my query to boost the relevancy. So as an example, if I just took what came back and ran that as a query, this generates really, really good results that are highly related to my original search. They're not the same because they're finding other things, but they're related concepts to my search. And if I run my initial search and then add this on as an additional filter, I can further limit down the results that come back. Again, instead of being based upon a piece of text, which may or may not actually be related to the domain I'm searching for, instead it's based upon a collection of related terms, and when you search for them all together, you boost documents that are related to many of these things much higher. So, next topic is document-to-document searching. So, the most common way to do this in Solr is using the more like this handler. The general use case is, instead of having a piece of text or a keyword that someone types in, I have a document that I want to use as a query. Obviously, if you pass in every term of that document into a Solr query, it'll time out. You'll get you'll hit an upper limit on the number of Boolean clauses you can pass in. Something bad will happen. It won't be performant. But if I've got a user profile, if I've just got a blob of text and I want to find recommendations, which is the common use case, or search results based upon it, there needs to be a mechanism to do that. So the more like this handler can do that. There's some other techniques you can use. I'll show one of those in just a minute. So how many of you guys in here have actually used the more like this handler? Looks like, that's a good number, about a third maybe. So for those of you unfamiliar with the more like this handler, you essentially pass in a query to the more like this handler. It scores all the documents, finds the top document that matches that query, and then looks for similar documents related to that document. This is the syntax for passing it in. You have to define, obviously, the request handler. You have a job description. In my case, job description, job title are the two fields that I actually want to find more like this terms in. I pass that in. These bottom two parameters, the more like this dot interesting terms and more like this dot boost are important, and you'll see why in a second. Those basically allow you to see the internals of what the more like this handler is doing. Instead of just getting recommendations back, you can get the terms and the weights associated with those recommendations so that you can use them for other purposes. So in this case, again, like before, all of these example documents are included with the Solr in Action book. So you can go to GitHub and download them. You don't even have to purchase the book, though. Please do. In this case, I ran a search for J2EE. What the more like this handler did is it found the top scoring document for J2EE, which is at the top, Senior Java / J2EE Developer. Based upon that document, it found this list of interesting terms over here on the right, and by me telling it to more like this dot boost equals true, it calculated a TF-IDF based score for how well each of these terms describes that document. And so you can imagine in a job description, there's tons of text. What it did is it reduced that text down to these words that it thought were relevant. And as you can see at the top, J2EE, Java, Senior Developer, Source Code, those all look pretty good. And then you get a bunch of garbage at the bottom. You've got words like is, for, a, to, and. If you had done stop word removal, those wouldn't be showing up. But in my case, I didn't. So you see that there's some good stuff, but there's also some very bad stuff. The beauty of this is that typically a couple of good things, if they're really relevant, will outweigh a lot of bad things just based upon the general TF-IDF. So you can throw some noise at Solr and it will handle it fine. It won't always work, but generally speaking, a little bit of noise is not a big deal. You're not going to be showing these terms to your end users. They're just being used internally to generate recommendations. And as you can see, at the bottom here, this is the list of recommendations that came back from the more like this handler. Core Java developer, application developer, Java architect, those all seem pretty relevant to me. I think it did a pretty good job with this example. One of the other nice things about the more like this handler is that you don't have to actually use a document that's in Solr. So in the last example, we ran a keyword search. We had Solr find the top document, and then it recommended similar documents based upon the document that was already in Solr. In this example, I'm just passing in some random text into Solr, and Solr is going to parse this text, treat it like it were a document, and then it's going to provide recommendations based upon that content. I'll caveat this with saying there's a neat trick in Solr where you can pass in for any request handler, I think any request handler, that takes in a content stream, you can actually pass in a stream.body parameter. So that's really useful, for example, for when you're indexing, if you want to add a document in Chrome or Firefox, you can add the document in using stream.body without actually having to issue a post request. If you're building an actual enterprise application, I would recommend doing an actual post here, but that's my caveat. But this works. So this is, I think this is from Wikipedia, just a general description of Solr. I pass that into the more like this handler, and I get back interesting results. So the interesting terms over here, search, Solr, features, enterprise, those are the terms out of that blob of text that were considered highly relevant, and then is, the, and, again, you've got these noise terms coming back. You can do things to try to make those go away, but they're always going to be there. And the recommendations that come back, enterprise search architect, senior Java developer, Java Lucene software engineer, again, it did a very good job of generating recommendations based upon a document that was passed in. At CareerBuilder, we have taken a slightly different approach. We've essentially customized it more like this handler to give it a different relevancy calculation. So we tried using more like this out of the box. We really, really wanted to get at the interesting terms coming out of the more like this handler. And unfortunately, TF-IDF just wasn't quite cutting it for us. Just like in that last slide you saw, and is all of those noisy words showing up at the bottom. We saw a lot of that, and we were trying to find a way to get more precise about the terms coming back. So what we did is we implemented a nice long pipeline to do that. And you can actually implement this yourself. You can do most of these things with things that are already built into Solr, but you just have to do them in steps and probably issue multiple queries to Solr. But the first thing we did is we send the document as a content stream to Solr, just like you will with the more like this handler. Then we perform language analysis on the content. Built into Solr, there's a language identification capability. We can harness that code and identify the language of the document. Once we've identified that language, we can create a language-specific part-of-speech detector using OpenNLP or using some other open-source technology or a paid-for technology. Generate parts of speech, and then remove everything that's not a noun. So if you think of most common use cases, the things you actually want to search for are entities. They're names, they're locations, they're, in our case, it's skills, it's capabilities for the employment market. Most other words are not useful at all. Sometimes adjectives can be useful, but in general, get rid of everything except for nouns to reduce the scope of the problem for the terms you're trying to find statistical significance for. Next, we do an analysis of those terms for statistical significance. So built into the more like this handler, you have TF-IDF. It's a reasonably good score, but in our case, we chose a different statistical significance measure. It's effectively, if you want to think of it like a z-score of a binomial distribution. It's what we're doing is we're passing in some foreground corpus, and then we're passing in a background corpus. And we're asking the search engine to look at all the stats inside of the Lucene index and tell us what is the probability of this term being more relevant in this foreground corpus than it is in the background corpus. So if you want to think of it conceptually, actually I might have it on the next slide. I'll come back to that. After we've done that, we return the top scoring documents just like the more like this handler does. So yeah, here's a good conceptual example. So I pass into my custom request handler. My foreground query is going to be for the category of software engineer. My background query is going to be all jobs that I have in the search engine. And then here's my content that's going to be passed in. What we're effectively doing is we're saying, take the likelihood of this term appearing across all documents, and then take the likelihood of the document appearing only in my foreground corpus. And for things that are statistically more likely to appear in my foreground corpus, weight those higher. And that's effectively what this calculation does for you. And so what you end up doing is, for this block of text here, Java, nurse, and is, are, was, were, yada, 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 these terms, Java, Ruby, PHP, and maybe document, would tend to show up higher in documents about software engineering than they would general jobs. Similarly, if I were to pass in category of nurse and pass in the same text, the terms that come back would be nurse, oncology, and any other nursing-related terms that were passed in. The word is, and a, all of those terms are equally likely to appear in all documents, so they would never come back. And the words that are very specific to the thing that I'm putting as my foreground corpus would be likely to come back. So conceptually, this is very similar to some of the previous discussions that we had a little bit ago about searching for a particular piece of text versus searching for a lot of related concepts together. You effectively, in a vector space, if you pinpoint one particular thing, for example, the term of nurse, if I just do a keyword search for it, then I'm going to find anything that has that term. That may not be what I want. What I want is something that has that term that is also related to something else that I'm looking for. In this case, we have a classifier at CareerBuilder. That's outside the context of this talk, but effectively we do some clustering to generate concepts. We pass documents into the classifier, and we get classifications out. So in this case, we have a job title classifier. We know that this content is about software engineering, and therefore we're going to anchor in the vector space. We're going to anchor to the, let's call it the concept of software engineering, and find all of the terms that are very close in the vector space to software engineering, and bring those back as the score. So that's the gist of what we're doing for foreground background corpus analysis. And I'm going to take questions at the end, so feel free to ask more about that. And good, plenty of time for questions. So those were a bunch of different topics that were all related to relevancy. To try to piece all of that together for you, this blue circle here is traditional search. It's what probably 90% of the people in the room are doing. It's out of the box with Solr. I do keyword-based searching, location-based searching, attribute-based searching. We also talked about recommendations, the idea of knowing something about either your user or a subgroup of users and using that information to affect relevancy, whether it's automatically generating a query based upon the group someone falls into, based upon the location they're in, or based upon specific information about that user. We can generate automatic queries for that user. If you intersect those two circles and you allow people to both search and also have their search augmented based upon what you know about them, you get this area at the top, which is personalized search. It's just like when you go to Google and you search for restaurants and you see restaurants in your city show up at the top. It's the same concept. That's where you get personalized search. And by doing both recommendations and search in Solr, you can easily blend the two together, whereas if you have a separate recommendation system, it's much more difficult to do so. Finally, we talked about semantic search. Semantic search is the idea of, instead of searching for text, searching for meaning. The person types in a query, you understand the query, you understand things related to the query, you understand what they're looking for, and you augment your query accordingly. And what I'm very interested in, obviously, is the intersection of all three of these, which is the center section. So someone comes to the site, we learn information about them, we personalize their search, we take what they're telling us, their keywords, their locations, we take those into consideration. Those are obviously the primary criteria because the user's driving that experience. But we don't just take what the user passed us as text, we also infuse it with meaning through some of these semantic search capabilities. And what I'm really interested in is seeing how this evolves in our industry, especially in the open source community with Lucene and Solr. Everybody's doing traditional search, just about. There's a subset of people in the community doing recommendations, even a subset of those doing recommendations in Solr. There's also a subset of the Lucene and Solr community doing semantic search, but it's not all coalescing together. So I'm guessing over the next 5 years, each of these areas is going to continue to grow and continue to get more traction, and that hopefully these circles will be able to, in not all use cases will you want them to, but in many use cases you'll be able to kind of collapse the circles down and have that middle section right there where you can do all of these and drive a truly, truly relevant search experience. You using personalization and semantic search. So a couple of takeaways. First of all, I've heard it in several talks here, so you guys probably get the first point at this time. But Lucine's inverted index is a sparse matrix useful for traditional search with keywords and locations, recommendations, and also discovering links between terms to be able to drive semantic search. Traditional TF-IDF keyword search is good when you're doing text search, but the best relevancy really lies in your ability to combine domain knowledge with user-specific knowledge. Domain knowledge driving your core relevancy functions and calculations, and the user-specific knowledge driving the personalized experiences. And then finally, the ability to understand user queries and not just treat them as text further enhances the search experience. We're done, and now I'm ready for questions. So,
anybody make a contrib of a matrix multiplier that be used inside of Solr?
So the question is, I was talking about Lucene as a sparse matrix, and he's saying that he hasn't seen anybody build a matrix multiplier, something to be able to do sort of calculations across the entire matrix at once, is kind of what you're asking for?
Yeah, it doesn't have to be the entire core. It could be, and more naturally would be, based on the query. So I get the query as a result. There's a matrix there, and then basically do the multiplication off that.
Got it. I haven't seen that. Typically, all the use cases I've worked with are effectively you've got the sparse matrix and you're performing a vector multiplication, right? You've got keywords, you've got some vector of factors that you're multiplying against the matrix by executing a query. I haven't seen anything that does, I guess, larger scale. Like you're saying, get a list of search results and then use that list to multiply against the matrix. It would be slow, I think, to do that. It's basically a sparse matrix that allows you to do vector multiplication against it, but matrix multiplication I think would be a lot more challenging. And I haven't seen anything like that. And I feel like it would not really be able to execute in real time. I could be wrong. Maybe someone can write some code and prove me wrong on that. But that seems like it's not the right use case. Maybe somebody disagrees. Yep.
I think I just missed it. Could you explain again how you extract the parts of the speech?
Yeah, I didn't explain that. The short answer is we pay a vendor for it. But there's a lot of open source technologies. I think OpenNLP's got part of speech extraction. Somebody using OpenNLP, can you nod if that's true? Yes. Okay. So download OpenNLP. You can pass the content into it. It will identify parts of speech for you, and then based upon, for example, if you just want to keep nouns, you just delete all the terms that aren't nouns, and then you could do that outside of Solr if you want. So you could pass your content to OpenNLP, take your original text blob, delete everything that's not a noun, and then just pass the nouns into Solr, into the more like this handler, or whatever you want to build, if you want to build something like we did to do a different kind of statistical analysis. But it's open source, but yeah, I didn't get into the nuts and bolts of that. All right, so the question is, in one of my examples, I basically OR'd a bunch of terms together, and when you do that, you obviously, any document that matches any of those terms will come back in the results and have to be scored. So the question is that okay? Is that too slow? Does it perform? The short answer is yes, it's slow, and things at the bottom of the list are going to be very irrelevant. They're going to match a single one of those terms, and if you have any noise terms in there, they're going to look very bad. My recommendation would be take things you know as part of your query, and if you're going to add these in, add them in later. Add them in is like add only the ones that you need onto the query. Ideally, a few of them, not a list of 50. And I mean, it should perform reasonably well as long as you don't go crazy with the number of ORs. But yeah, ORs in Lucene and Solr are not fast, especially as you add more and more of them, because it's doing a union of all of those bit sets every time you add another OR. So I would not recommend just ORing a bunch of things together. You would be better off ANDing the ones you can. But yeah, I mean, it's a good point. The question is, when I was describing relevancy as a linear function, meaning having the relevancy parameter, having the keyword parameter, having the category parameter, did I consider using machine learning to derive those weights as opposed to tuning them manually? On the location example that I showed, where software engineers are very insensitive to moving for a job and food service workers are, I used, what was it? Logistic regression with stochastic gradient descent and Mahout to initially come up with those variables. It didn't work well at all because I was mainly focused just on location, and really that works better if you've got all of these parameters in. So it's definitely a good approach, and it is definitely something I'll do again in the future. At the moment, we've manually tuned them based upon what we know about the user. So we derive the location information. That's really the only one that's context sensitive right now. The other ones that we have are more universal, but definitely over time I want to get a lot more customized for each job title, so that location and keywords and all of the different relevancy parameters can be tuned based upon the context. And I would probably use machine learning to do that. Maybe some more logistic regression or something like that. Yeah. It's a great question. So the question is, we're doing very intelligent, thank you for saying that, stuff with relevancy. I just get up here and talk. It's not actually that smart. I just put stuff on slides and that's all. But the question is, how do we actually evaluate that we're doing well with relevancy? You can tune the parameters all day long, but if your users aren't happy, or if whatever your criteria for measurement is not good, then you're failing. So the short answer is, for job search, historically we have measured relevancy based upon applications. Meaning the general concept is, if I'm showing relevant results to a job seeker, they're more likely to apply to that job. And that's been our primary driving factor for that relevancy. It's a good theory most of the time. The only problem with it is it incentivizes you recommending things and tuning your relevancy for people who are very indiscriminate job appliers. So there's some people out there who apply to 1,000 jobs a day. And there's some people who apply to 2 or 3 or 1 because they found the right job. And so if we want a really, really finely tuned relevancy calculation that is basically very good at finding specific matches, that's probably not the right metric, because we're incentivizing ourselves to modify the relevancy calculation such that people who apply to thousands of jobs are going to be more likely to apply. In our business case, that's historically been a good thing, because most companies want lots of applications and they're happy to take 30, and if there's only 5 good ones in there, they're happy to just get the flow of candidates. That's starting to change in our industry, so we are starting to get more focused on very good matches at the expense of lots of job applications, for example. So in that context, we're starting to look at things like precision recall curves and similar scores, where we can build a document set and test our algorithms over time as we improve them to see that precision and recall are going up in tandem. We're not quite there yet. We're still a little bit married to the idea of the more people applying to jobs, the better we're doing. But we're starting to break that model a little bit. And I think it will ultimately yield more precise results at the expense of less of people applying to jobs. But maybe that's a good thing. Sure. So the question is, how do we actually test it? Which was the first question. So I'll answer that now. Yeah, we A/B test everything. Whenever we release a change to our relevancy calculation, we run an A/B test. We have a control group, experiment group, and we make sure that the experiment group does statistically better than the control group. And if so, then we turn it on and leave it on, and then we move on to the next experiment. And it's easy for us to A/B test like that because we have millions of searches an hour, and we have over 1 million job applications a day. So I can turn something on at 1 or 2% of all job seekers coming to our site, and within a day or even a couple of hours know what the statistical significance is. Most people don't have that luxury. All right, I think I'm about out of time. Thank you guys for coming.